Question 1, part B. A nucleus of mass 3.93 times 10 to the minus 25 kilograms. Let's use the blue pen. Show better. Is stationary with respect to observer. Okay, there it is. Undergoes fission. So that breaks up. It breaks up into 2 equal parts. Each, no, with total kinetic energy. Kinetic energy total equals 200 mega electron volts. Remember, 1 electron volt, 1.6 times 10 to the minus 19 joules. The 2 parts are brought to rest. That doesn't say how that is done, but obviously it's done somehow. Calculate the total decrease in mass in kilograms, and therefore calculate the individual rest mass of the 2 equal masses. So, what are we trying to do? Calculate the total decrease in mass. So, who have we got before? We've got a nucleus, we've got after, and these have got kinetic energy somehow. We want the decrease in mass. Okay, so fission question, energy related to change in mass. So there's our Einstein's favourite or famous equation. In this form, our energy, and you use delta E. Do you just use the E here? It's just the E. So the change in energy equals a change in mass times the speed of light squared. So we want to know the change in mass. So what's the change in energy? So before, well, we've got no kinetic energy, we've just got the rest mass energy. After, we've got kinetic energy, which has been lost somewhere by bringing them to rest somehow. We've got then the individual masses. So this looks just a straightforward application of that principle. So our delta M equals our change in energy divided by c squared. So that's 200 mega electron volts divided by the velocity of light squared. So let's put this in SI units. Now, right at the beginning, remember the paper said put everything into SI units. So that's 200 megas times 10 to the 6. An electron volt, 1.6 times 10 to the minus 19 joules. That comes from the potential energy of an electron as it moves through 1 volt. So it's that charge on the electron, but just in terms of a joules number, divided by speed of light squared, which we know is 3 times 10 to the 8 meters per second. But it's given, if you can't remember that. Again, my calculator is sitting somewhere where I can't get it. I should have brought that over. But we can do that calculation.
Speed of light squared.
I always
do that.
Yeah, let's not forget that. Speed of light squared, so that's about 10 to the 8 times 10 to the minus 19, so that's about 10 to the minus 11 on top. And then we've got 3 squared is 10, so we've got about 10 to the 17 on top, on the bottom. 10 to the minus 11 divided by 10 to the 17 is 10 to the minus 28-ish, something like that. We know it's going to be small. We're talking about nuclear masses here. We're not talking about large changes. And it's worth thinking, well, just compare that with that. We started with something that's about 10 to the minus 25 kilograms. We've lost about 10 to the minus 28, a thousandth of it. That's sort of right order of magnitude. You know, if that number were bigger than that number, we start thinking, hang on, something's not right here. Okay, so that's total decrease in mass, and therefore individual rest mass of the two equal masses. So here's our total mass. We therefore have lost, here's what we started with. So mass to start is 3.93 times 10 to the minus 25 kilograms. Mass to end with, total, equals that minus whatever this is. We need a calculator there. I'm making that number up. So that's what we end with. Yeah, so we lost that. So this is split into two equal parts. So mass to individual equals 3.92 divided by 2, which is going to be 1.96 times 10 to the minus 25 kilograms. But remember, I'm making that up. Okay.